Hi, my name is Isha Garg and I will be talking about our work titled DCD-SNN, using DCD to distribute spatial information over time for low latency spiking neural networks. This is work jointly done with Saeed Chaudhary and our advisor is Professor Kaushik Roy here at Purdue University. The motivation for this work stems from the fact that deploying deep neural networks is tremendously expensive in terms of power consumption. Let's take an edge device use case, that of a smart glass. We want to ensure that a small on-device battery can sustain it for a long time. To this end, we take inspiration from the brain and train spiking neural networks, or SNNs. SNNs distribute computation across spikes spanning many time steps. Spikes are digital values of 0 and 1, denoting absence and presence, which results in computational efficiency. However, SNNs suffer from high inference latency as the spikes need to propagate to the final layer. In this work, we tackle the inference latency issue by focusing on the encoding scheme used to convert pixels to spikes. The standard scheme is called Poisson encoding. It compares each pixel value to a random number generated between 0 and 1 at each time step, and spikes if the pixel value is greater. This scheme does not really utilize the time axis well and treats all time steps as equal. We propose a new encoding scheme that efficiently utilizes time for breaking down and reconstructing pixels as spikes. Our encoding scheme consists of two phases, deconstruction and reconstruction. In deconstruction, we break down the input X into a weighted sum of pre-selected basis images. Here we show a 1D input vector and 5 bases concatenated as columns of a transformation matrix T. The dot product of this results in the intermediate representation shown in red and denoted by Y. The second phase, called reconstruction, reverses this. It takes Y as input and reconstructs X over time. At each time step, we feed in a single basis vector modulated by the intermediate representation and accumulated over all time steps. At the end of all time steps, we note that we have recovered the true input X. Here we show how the reconstruction is spread over time results in spikes. Let's consider time step 1, where Y1 modulates the first basis vector. This modulated vector is fed to an integrate and fire neuron. The neuron keeps integrated the modulated basis vectors until they reach a threshold and then it emits spikes. This ensures the input to the first layer of the neural network are spikes for efficiency. The desirable properties of the ideal set of bases are that they be orthogonal to avoid interference. We show that a random matrix results in accuracy drop that can be recovered by using an orthonormal transformation matrix. The second desirable property is that the bases are ordered by the contribution to reconstruction of input. We show later that this allows us to drop the non-significant bases in order to do resource adaptive inference. These two properties are satisfied by both the PCA transform and the discrete cosine transform, which give similar results. We use DCD since it has the additional benefit of being dataset independent. Taking inspiration from JPEG compression, we perform DCD and PCA on 8x8 blocks of the images of CIFAR10 with no overlap and visualize what they look like. The choice of block size and overlap are hyperparameters, and we show that using a 4x4 block with overlap of 2 resulted in the lowest accuracy drop compared to an ANN. We now show results on SNNs trained with our encoding scheme. This set of results is for VGG9 trained on CIFAR10. We show the effective time steps and accuracy for our scheme in blue versus Poisson encoded SNNs in orange. At just 32 time steps, shown by the dotted line, DCD SNN has converged to near full accuracy, whereas Poisson encoded SNNs do not converge at all. We believe this is because we convey salient information early on. We have DCD blocks of size 4x4, which means we have 16 time steps of one cycle to convey the full information of X. On the right, we have a VGG9 trained for 3 cycles. We show here what happens if you limit resources during inference by limiting cycles to 2. We pass the entire first cycle and then show the effect of adding each one of the 16 bases, one by one in cycle 2. It can be seen that most of the accuracy is gained with the early time steps corresponding to the more significant bases, while the later time steps corresponding to the lesser significant components show saturating accuracy gain. This means that we can drop the later components during inference, allowing us to adapt to limited resources after deployment. We now show comprehensive results for CIFAR10, CIFAR100, and Tiny ImageNet datasets. We compare with ANNs and Poisson encoded SNNs trained on pixels and on DCD coefficients. For all networks, DCD-SNN converge to equivalent or better accuracy than Poisson-encoded SNNs while cutting down time steps for training and inference by more than half. The reduced latency allows us to scale to large datasets such as Tiny ImageNet, which is traditionally proven tough, with an ability to achieve convergence in just 48 steps. This reduced latency, along with spiking characteristics, results in DCD-SNN being up to 1.75x more energy efficient than ANNs. Thank you for listening to my talk.